So in the last class, we were looking at the conditional density of a Gaussian random vector. So let's look at the proof of that. Okay, proof. Okay, so essentially, I have to write the joint density of xy and divide it by the marginal to get the conditional, right? So now what will be the joint? So for example, if you have xy, two random vectors with the corresponding covariance given by kx, ky, kxy, and kxy transpose. I think something like this, right? So I think it should be a transpose. Yeah, it will be a transpose of this. Okay, so let me call this as something like B, C, C transpose D. Okay, so there are four matrices like this. So with this notation, let's get started. So what will be the joint density of xy? So if xy of xy would be exponential minus half times xy transpose. So that is x transpose y transpose, right? The okay, times the covariance k inverse times x transpose y transpose whole transpose, right? So this is the exponent divided by 2 pi power the number of terms, right? So you have n plus m terms by 2 because x is of dimension n and y is of dimension m, right? Square root of determinant of k inverse. So is this okay? I mean, this is fine, right? Fine?
Yes, sir. Yes, sir.
Okay. So now I have to write the inverse of k, right? So how do you write the inverse of k? So what do you think is k inverse? So k inverse, I'll write, okay, sorry, I think I made a mistake here. So let's use
Sir,
the, yes.
it should be determinant of K, not K inverse. Determinant of K inverse should not be there.
Determinant of k, that's correct. So yeah, this should be, let me just think, is this, yeah, this is correct. Yeah, this should not be determinant of k inverse. Okay, so okay, fine. So I'll write k inverse as BC C transpose D. Okay, is that fine? So if a matrix A is symmetric, A transpose is equal to A, then the inverse, if it exists, is also symmetric. Okay. So I'll call that inverse as this matrix BC transpose D. Is that fine? Of course, there is a way of finding.
Sir,
Yes.
sir, one question not related to this.
Uh,
Like, sir, in the previous lecture, you said that if any matrix is symmetric, sir, then
Yes.
is it necessary that it should be positive semi-definite?
Not necessary.
Okay. Or
Symmetric matrices need not be positive semi-definite. Hmm?
okay. So
So
is
there
it
is.
inverse true? Like, if it is
Huh?
positive semi-definite, then it will be symmetric.
No, not necessary.
Okay.
Even that is also not necessary. See, how do I put it? Yeah, you take a matrix, you can give always a counterexample, right? This is a matrix. It's not, okay, sorry, I'll just do this. Is this symmetric? It's not symmetric,
Okay.
right? But if you multiply by xy, what do you get? You get y and 0. And then you have xy, right? So you get xy. So no, this is not symmetric. No, and not necessary. You can give us a counterexample. Okay, I
Okay.
don't. Let's not worry about the counterexample now. You can give counterexample.
Okay.
Okay, so now I can write the exponent in the following way, right? So the exponent would be minus half, okay, x transpose y transpose k inverse. So k inverse is what? This matrix, right? A, B, C, B, C, C transpose D. So if I plug it in there, I get the following, okay, Ax transpose Bx plus x transpose Cy plus y transpose C transpose X plus y transpose dy. Okay, this would be the exponent. Do you agree? Fine. So now what is f of x given y, of x given y? This will be the of the form something like f of some phi of y, right? That is like f of xy divided by phi of y, this thing, and some other function here, right? So some function. This is the general form. Do you agree? So now, if you look at the this expression here, right? This expression, the exponent here, I can rewrite the exponent in a slightly different fashion. Okay, so for example, if you look at this term, right, y transpose dy, that is a function of y only, right? I can pull that out of the exponent and call it as phi of y. So now I can write this as some phi of y. We will see what phi of y is times we'll have the remaining, right? So what is the remaining? We'll have exponential of minus half times, right, x transpose bx plus x transpose cy plus y transpose c transpose x. Okay, this is what we have. Okay, is that fine? Fine? Fine, right?
Yeah. Yes, sir.
Okay,
Yes.
yeah. So now I'll just complete the squares in the exponent to get the following. Okay, so again, I can write this as p of y, okay, exponential of minus half. I can complete the square as follows. So I can write this as x plus, okay, so b inverse c y whole transpose, right, this into this whole thing into x plus b inverse cy, okay, plus this will be plus y transpose c transpose b inverse cy. Okay, this is something, this is how I can complete the square. Okay. Okay, now again once you complete the square, again you can observe that this term is independent of x, so we can just pull that out and absorb into phi of y. Okay, so now what is it that you have gotten? So we need to describe this by a mean and covariance, right? So what should be the covariance and what would be the mean, right? So I think I missed the okay, sorry, this there is a b here, okay, in between the b. Okay, so now I can write this as follows, right? This is some phi of y, let me call this as phi dash of y, okay, exponential of minus half. Okay, now I can write this as x plus b inverse cy transpose this thing. Okay, of course there are constants, for example divided by 2 pi power something, all that. So I have observed that into phi dash of y, so this depends only on y. Now if you look at f of xy of xy, I can write this as f y x given y of x given y into fy of y, right? So now this is only a function of y, and this is something that depends on both an x and y. And all that we have to care about is the exponent of this. The moment I know the exponent, essentially I'll know what the distribution is, right? By observation, what can you say about the mean and the variance or the covariance of this thing? F of x given y. So the mean is B inverse. This is minus B inverse Cy is the, sorry, not y. Cy is the mean. What will be the covariance? Covariance is B inverse. Okay? Because x minus mu whole transpose K inverse times x minus mu is the exponent of a Gaussian random vector with mean vector mu and covariance K. So by that observation, I can write the conditional density as Gaussian with this mean and the covariance. Okay, so it's mostly algebra. That's what you end up doing. So what can you say from this? So essentially, it says conditioned on y, right? Conditioned on y. X is Gaussian with mean B inverse Cy and covariance B inverse, right? So that means I can write X as, okay, conditioned on y equal to this y, one part is fixed, and you should have a mean of, let me write it like this. Okay, now I have to see what G is. Conditioned on y, right? So this should be Gaussian. We should have a zero mean, because when you say expected value of x given y, I should get B inverse Cy. So given y, this is a constant. G should be minus B inverse C. Okay, that will be G. Okay, so what will be the covariance? The covariance of this would be B inverse. So the covariance of this V should also be B inverse, because I'm subtracting. When you look at the covariance of x given y, you have to subtract the conditional mean from x and multiply it with the transpose to get and expected value to get the covariance. So the covariance will be this. So in general, if you have jointly Gaussian xy with certain joint covariance, I can write the relation. I can write x and y through this relationship. Okay. Is this fine? Any questions? Are you guys there, or did I?
Yes, sir.
Okay. Any questions?
Sir, here the covariance of G is I, right?
No, G is a matrix. It's a constant. Right? G equal to
Okay.
this. V is Gaussian. Think of it as a noise. Okay. Fine. Okay. So why is this useful? For example, I can tell you. Suppose if you have xy as jointly Gaussian, and if I want to find so something like this, right? Y equal to h x plus w, right? I want to find an estimate of h given what I know x. So that expectation would be that estimate of h hat would be expected value of what is h hat? H given y equal to the observation, right? So this will turn out to be an MMSE estimate. So now if I know the joint distribution of h and y, right, turned out to be Gaussian with certain covariance, then h given y conditional distribution will also be Gaussian with certain mean and covariance, which can be found using these expressions. And now the expected value of that is one of the term like this, B inverse Cy. Okay. So essentially it turns out h hat is, in this case, is some constant A or some constant matrix A times y. That will be your estimate, MMSE estimate of h. Okay, so we will see this a little later maybe, but just to give you a quick reason of why we need to look at all this in the context of, for example, signal processing or communications, this is the reason. Okay, so now let's look at let's move on to what is known as a Gaussian process. Okay. Gaussian processes. Okay, so this is an important topic, but some of the things I'll skip because it involves Fourier transform and Fourier series, especially, which I'm assuming that you know. So I'll leave it as some of the aspects as a homework problem. So you have to figure that out. Okay, so what is a Gaussian process? So you know that any stochastic process is a collection, right? Xt such that T belongs to some set T. That is it's a stochastic process. When do you say that it's a Gaussian process? Meaning a special kind of stochastic processes called Gaussian processes. When do you say that? So let's define it this way. So essentially, if you look at, you fix, let's say this is your time axis, think of T as time. You pick certain time instance, k of them, okay, t1, t2, t3, t4, and so on, k of them. And if you look at x of t1, x of t2, x of t3, and so on, x of tk, those are random variables. A collection would be a random vector. So if that random vector is a jointly Gaussian distributed, then we say that no matter what k and what these instances are, then we say that the process is a Gaussian process. Okay, we say that x of t, okay, so t belonging to, let's say, some t is a Gaussian process if for any k belonging to n, that means you take any integer, okay, and all choices of epochs, all choices of time in, sorry, I'll call it as epoch or time instance. I'll use the terminology in the book. It's epochs. Epochs. What are those epochs? T1, T2, etc. Tk. So these are epochs. That is the time instance. Okay. If you look at x of T1, x of T2, etc., x of Tk is jointly Gaussian. Okay, is that fine? Any questions? You need to understand this, pretty well. So, any questions? Yes. Any questions?
So here, this is same as the one we defined for converting joint like Gaussian vector to Gaussian random variable.
No. See, the flow was this, right? So we introduced what is known as Gaussian random variable, okay, and then we move to what is known as Gaussian random vector, right? That is basically you give x1 through xn, it's called jointly Gaussian if any linear combination is a Gaussian random variable, right? That's how we moved, and then we looked at joint distributions and so on. But now, if you have I have to define what is known as the Gaussian processes. So the way to do that is somehow convert, this is like think of it as a continuous time process. Think of speech processes, speech signal, right? Well, it's not really a Gaussian process, but the noise in the speech process, for example, let's say you speak and then it gets converted into electrical signal and then noise gets added. So you can think of that process as a Gaussian process, meaning, well, how do you define that? So you don't know how to define some function as Gaussian, right? But you know how to define a bunch of random variables as jointly Gaussian. The way you do that is convert something that you don't know into something that you know. How do you do that? Sample. You take k and sample them, you get k random variables, you say that it's jointly Gaussian. Is that fine?
Yeah, yes, sir. So like
Right?
in okay, so like in random vector, there are random variables x1, x2 up to xn. So here T1, T2 is different, and we are substituting like TX1, TX2. Sorry, X T1, XT2, and something like that.
Yeah, it's like this. So, for example, I can think of it as like this, right? So you have a signal like this, which is Gaussian. So let's say x of t, and okay. So let's say this is your time axis, okay, and you are taking time instance. Let's say t1 is this, t2 is this, t3 is this, t4 is this, t5 is this, and so on, okay. And then you are looking at the amplitudes. Those I will call it as x of t1, x of t2, and so on, okay, and so on, right? So these x of t1, x of t2, and so on, x of tk are random. It corresponds. It's a random vector, right? For a fixed t1 through tk and k. If I fix k and t1 through tk, I'll get x of t1 through x of tk, which is a random vector. If that random vector is a Gaussian random vector, no matter what k is and where you pick these t1 through tk, then we say that the process is a Gaussian process. Okay, it's kind of weird in the sense we don't know how to generate this kind of a process, but we started out by saying, well, this is what I call a Gaussian process. We need to investigate whether this makes sense or not, right? I mean, if such a process does not exist and we may not be able to construct it, then the whole exercise is useless, right? So what we are going to do is we'll study a few other things and we'll see how to construct such a thing. Okay, did I answer your question?
Yes, sir. Yes, sir.
Okay.
So, sir, one more thing. So this X1, XT1, XT2, this will follow a Gaussian distribution.
Yes, so jointly Gaussian. What do you mean by jointly Gaussian? You have to specify two things, right? It's the mean vector and the covariance, right? So that means if I specify these two things, then the entire joint distribution is known. Do you agree?
Yes, sir.
That's why Gaussian is beautiful, right? So you just need to know only two. It's beautiful for other reasons also. We'll see what those reasons are. But yeah, so this is what it is, right? Okay. So
Hello,
let's
sir.
look at yes.
So here xt1 and t2 are random variables, right?
X
Individually,
of t1, x of t2, yes, they are random variables.
and they are Gaussian random variable.
Yes, so it is jointly Gaussian, so it has to be Gaussian. Can you prove that x1 through xn is jointly Gaussian? Can you prove that x1 is also Gaussian?
We take all the other things as 0.
Ah, exactly, right? Yeah, in your linear combination, you take 1, 0, 0, and you use that as a linear combination. Then you'll get x1. x1 by definition is a Gaussian random variable. Yes, you are right.
Is it both ways, sir?
Meaning?
I mean, jointly Gaussian implies each is
Yeah, you have proved that now, right?
yeah, correct.
Each one is Gaussian. So you yourself have proved that, yes. Okay. Any question? Any other question? Okay. So now, when we studied Gaussian random vector, we talked about covariance, right? Or when we looked at x1 comma x2, we saw what is covariance. If you have a Gaussian process, what do you mean by covariance? So essentially, the way to do that is, you take two time instances, let's say t and tau. You have x of t and x of tau, two random variables, and I can see what is the covariance of that, right? So the covariance will depend on both t and tau. So it's called a covariance function. Okay, so the covariance function, I'll call this as kx of t comma tau, okay, of a stochastic process. Well, this is very general definition, but when you apply it to Gaussian, it makes things very simple. Okay, stochastic process. Let's say x of t belonging to t, right, is defined as, how do you define this? So, okay, let me write it here. So k x of t comma tau is defined as you take expected value of x of t minus the mean of x of t. X of t is a random variable times x of tau minus the mean of x of tau. Right? So this is the covariance function. This is true for all t comma tau belonging to tau. Okay. Okay. Is that fine? Is that fine? Okay. Now let's see what happens if this is Gaussian process. So
Hello, sir.
suppose yes.
Sir, here when mean is 0, I mean E of xt and E of x tau is 0, then it will become autocorrelation, right?
No, right? Why do you say that it's the mean is 0? It will become autocorrelation. Autocorrelation is when you take t equal to tau.
T.
Sorry, yeah, it is this itself. In fact, this itself is an autocorrelation covariance function. You are not taking two different stochastic processes and looking at the product expected value, right? You are taking the same stochastic process and looking at the covariance. So it's called the autocovariance function.
Yes.
Okay. So if you have two different, let's say x of t and y of t, and then you look at x of t minus expected of x of t into y of tau minus expected of y of tau, then we say that it's cross covariance. Okay. Yeah. So now, if you have, let's say, you take a Gaussian stochastic process, x of t1, x of t2, and so on, x of tk. That means you fix k, any k. K could be 100 billion or k could be 2, right? And the time instance t1, t2, etc., tk is arbitrary, any time instance, no matter what, right? So this is jointly Gaussian, right? It's jointly Gaussian. So what will be the mean? The mean vector will be easy, right? So it's expected value of x of t1 and so on, expected value of x of tk. Do you agree? Right? Do you agree?
Yes, sir.
What is the correlation covariance function? See, first one would be x of t1 times minus expected value of x of t1 times expected value of x of t1. So this is nothing but kx of t1 comma t1, right? All the diagonals will be like that, kx of tk comma tk, right? So what will be the ijth entry? Ijth entry would be kx ti comma tj. Do you agree? And so on. So what this implies? This implies that you need to know the mean function of the stochastic process and you need to know the covariance function of the stochastic process. If I know these two, that will describe the entire distribution, joint distribution of a Gaussian process. Okay, so essentially, I'll just refer, I won't write this. This is theorem 3.6.3 in the book. Okay, essentially says that if you have a Gaussian process, the covariance function and the mean function for each time instance tau and t describes or specifies the joint distribution of this Gaussian joint probability density for all possible combinations of these random variables. Okay, is this understood? Fine. Yes or no?
Yes, sir.
Yes. Okay. Any questions? So this is important. Okay, so you should understand what this is. So essentially, if I know the covariance function and if I know the mean function, I know the mean of all the means of any random vector, right? And I also know the covariance of that random vector. So means, covariance function and mean will specify the joint distribution. Is that okay?
Yes, sir.
Okay, so now let's do the first construction. So how do you construct a random stochastic process, right? Gaussian stochastic process. So this is the first example in the book regarding this. So this essentially talks about something that we have already seen, discrete IID Gaussian process. Okay, so what is this? This is very easy. So you have to describe this by W of n such that n belongs to Z. You know what Z is? What is Z? Yes?
Set of integers.
Set of integers. Okay, it's two-sided. -1, -2, and so on. 0, 1, 2, 3, and so on. Okay, so you have this stochastic process where each samples W of 1, W of 2, and so on are chosen in IID fashion from Gaussian distribution, zero mean and variance sigma square. Okay, so now what is the mean process? W of n. Let me call this as mu of n, which is 0 for all n, right? So the mean function is 0, no problem at all. Now the next thing that I need to know is the covariance, right? So I'll take two time instance, n and k. Okay, don't get confused with the k that I chose earlier. So this is the covariance function of this stochastic process at time instance n and k. So what is this? This is nothing but expected value of W of n times W of k. What can you say about this? See, whenever n and k are not equal, they are independent random variables with zero mean. So expected value of the product becomes product of expected values. The expected values are 0. Therefore, it will be 0. It won't, whenever n equal to k, this will be W square of k, which is variance sigma squared and Kronecker delta, right? So this, you know what Kronecker delta is? This is not the Dirac delta. Okay, so I'll write this here. 1 if n equal to k, 0 otherwise, right? So this is a simple process like this. So now how do you write the joint density? It's pretty easy, right? So if you take the joint density of k random variables, let's say W of n1 and so on, W of nk of W1, etc., Wk, this is the joint density. This is simply 1 by 2 pi sigma squared whole power k by 2. There are k random variables. Exponential of this is IID, right? So it will be 1 by 2 summation I equal to 1 to k Wi squared by sigma squared. Okay, so this is how you describe the joint density regardless of what k is and what n1 through nk are, right? Regardless of that, this is the distribution. So you know pretty much everything about this stochastic process. In fact, yes.
Sir, like, can you explain once? Like, here you have said there are two times n and k.
So this is the covariance, right? N and k. But whenever n is not equal to k, this covariance is 0. That means if you look at the covariance matrix of k random variables, the diagonals will be non-zero. Otherwise, everything else will be 0.
So my question is, like, two time instance of the n comma k you're telling, then what is this n?
N is Wn, W of n, that is the random variable. So you take the stochastic process and look at what is the amplitude at time n. Discrete time. So think of it as a discrete time stochastic process. It's not a continuous time stochastic process. Other thing is k. For example, n is equal to 2 and k equal to 3. So you are looking at W of 2 into W of 3. Of course, expected value is 0 because they are not correlated, right? Did I clear your doubt?
Sir, maybe if you use m instead of k, it will be fine, sir. Because you have used k for number of vectors.
Okay, fine. If you are. Okay, so I'll just use a different color. M, M, M. Fine. You're okay with this? Ayush?
Yes, sir. Yes, sir. Yes.
Okay.
Sir,
Yes.
sir, will the diagonal elements be equal, sir?
Yes, in this case it's equal, right? It's sigma squared. Yes. So essentially the covariance will be sigma squared time identity. So the dimension of that matrix depends on K. If K is 10, it will be 10 cross 10. If it is 100, it's 100 cross 100. It doesn't matter which 100 samples you pick here because they are IID. Okay. Let's look at another example. Maybe it will be clear. This is an example which is again a discrete time example. So what I'm going to do is I'm going to write this as S of n, which is the sum. Excuse me. Which is the sum I equal to 1 to n W of I. Okay. This is some process. Okay, so this W of n, right? So these are all IID random variables. Okay, is that fine? These are all IID random variables. I'm going to sum them to get a stochastic process which is S of n such that n belongs to n or n greater than or equal to 1. Okay, this results in a stochastic process. This is called the sum Gaussian stochastic process, right? Sum Gaussian process, Gaussian sum process. Okay, now what can you say about expected value of S of n? This gives me the mean process, right? Mean of n. This is 0 because expected value of Wi is, Wi is for 0 mean Gaussian process. So it is 0. Now what is the next thing? We need to look at the covariance, right? So what will be the covariance? K, covariance of the sum at 2 points. Let's look at Nm. Okay, I'll change the notation. So this would be expected value of S of n times S of m, right? So S of n would be I equal to 1 to n Wi. S of m would be j equal to 1 to m Wj, right? So this is what we get. Okay. So now I can write this product as summation over all ij from 1 to n and 1 to m, W of I, W of j. But expected value of W of I, W of j will be non-zero provided I equal to j. So this will be I equal to j. Then only you will have this thing, right? So I equal to 1 to, well, I equal to j, but whether should be go till n or m, it depends on whichever is minimum, right? So nm, right? So expected value of Wi squared is sigma squared, right? So this is nothing but, right, the minimum of n comma m sigma squared, right? The covariance of n comma m is whichever is the minimum, n or m, times the variance is the covariance, right? Is this fine? So now, this leads to an interesting notion called stationarity. Essentially, this covariance depends on what n and m are, right? For example, if n is 3 and m is 2, then it's 2 times sigma squared. If n is equal to 100 and m is equal to 200, it's 100 square sigma squared. So the variance changes depending on what n and m you choose. Okay. Okay, the next one is very, very important. I think if you are into statistical signal processing, you kind of encounter this very often. It's called the Gauss-Markov process. Okay, heard of it?
No, sir.
Anyone? No. This is called. Let's look at an example of a Gauss-Markov process. So essentially, again, this is a stochastic process. X of n belonging to z plus. Okay, that means 0 included. Okay, so I'm going to define this as follows: x of n plus 1 is equal to alpha times x of n. Alpha is a fixed number plus w of n. Okay, and n belongs to z plus, and x of 0 is 0. Okay, I should also describe what w of n is. So w of n So W of n is an IID. What happened? Okay. Hey. Okay. I'll write here. So W of n okay. It's IID, okay, with Gaussian zero mean, okay, and variance, let's say sigma square. Okay, this is the Gauss-Markov process. Okay, is that fine? So I can, you know, if you are into signal processing, I can write this in a slightly different fashion. So it's almost like giving W of n. So there is some noise. Okay, I'll just add the noise with the delay, right? So this is the delay, and this is x of n, and all that I do is when I delay it, I'll multiply it by alpha. Okay, this is how it looks like, right? You delay it, multiply by alpha, and add it to W of n to get x of n plus 1. Okay, and keep doing that. So this is how you get it, but now I need to see what is the mean of this process. So let's look at what will be x of n. I'll write it recursively what this x of n is. X of n would be something like this: W of n minus 1 plus alpha times W of n minus 2 plus and so on. The last one would be alpha of n minus 1 W of 0. Okay, so this will be x of n. How did I write this? Well, recursively, alpha into x of n. X of n is alpha into x of n minus 1 plus W of n minus 1. So keep doing that, you will get it. Okay, so this implies the mean of x, right? The mean process is 0 because it's the sum of Gaussian IID random variables with 0 mean. Okay, what will be the covariance, right? So let's look at the covariance now. So expected value of x of n times x of m. So what I will do is okay, so let's look at this. So if I just do this, right? Okay, so x of 1 times x of 2 is same as x of 2 times x of 1, right? So what I will do is I'll slightly modify the way I'm going to write this. I'll just write n plus m, okay? Because if 1 is greater, then I can just you know commute it and then write it as x of n times x of n plus 1. Okay, so now okay, I'll give this as homework. I think even the textbook you know, he doesn't give you the solution, but this is how it looks like: alpha power 2n, or I'll do it divided by 1 minus alpha squared. So how do you write this? How do you you know how do you prove that this is true? Yes. Yes.
Sir, it will be like summation alpha square power n.
See, x of n plus m, I can write it in terms of x of n, right? Do you agree? See, what is x of, okay, let's look at this as x of n plus 2. This is alpha into x of n plus 1 plus w of 1, right? Is that correct? That's the notation that I have used. Yeah, w of n. Okay, this is sorry, n plus 1. But this is equal to alpha into alpha x of n plus alpha into w of n plus w of n plus 1. Okay, so now x of n times x of n plus 2 would be what? Alpha squared x squared of n, right, This is what we have. So essentially what ends up happening is that then alpha times x of n into w of n plus x of n into w of n plus 1. Okay. Now, x of n depends on w of n and w of n minus 1 and so on, right? It doesn't depend on w of n plus 1. So they are independent. So when you take expected value, the expected value of w of n plus 1 is 0. Therefore, we need not worry about this term, right? Only we need to worry about these two terms. So what is x of n? X of n, so I can write this as alpha squared x squared of n. This is an example, so how you can generalize this. Alpha times x of n is what? Alpha times x of n minus 1 plus w of n. Is that correct? So I've written n plus 1 is the previous. Okay, so n plus 1 is the previous. X of n is x of n minus w of n minus 1. So x of n also it doesn't matter. So this is what you get, because x of n and w of n are independent. So when you take expected value, this is what you get. But x squared, x of n is something that I already have written, right? So x of n is given by this. All that I have to do is square this, right? So what will be the square of this? This squared plus this squared and so on. It will all be the squares. Expected value will be sigma squared times 1 plus alpha plus and so on, alpha n minus 1. It's a geometric series. The cross terms will anyway will be 0. So you have a geometric term here, right? That's why you get 1 minus alpha power 2n by 1 minus alpha squared. There is an alpha power k because, okay. So now this is expected value of this whole thing will be alpha squared times expected value of, it will have 1, well, there is no expected, so we can take the expectation out. I mean, you can take the expectation in and write this. Alpha power x of n is what? Alpha power n minus 1. So this is, well, into sigma squared. So this is alpha squared sigma squared times what? You get this geometric series, right? 1 minus alpha power n divided by 1 minus alpha, right? Is that correct? Yeah. Do you agree with this? Maybe check. I might have missed out some terms, but I think the flow is correct. Okay. I might have done some algebraic mistake in between, but otherwise the flow is correct. Is this fine? Yes.
Sir, alpha is always less than 1, sir.
Okay, that's a good question. So what happens to alpha here, right? So if alpha is not less than 1, in fact the mod alpha should be less than 1, then these things make sense. Okay, as you increase m, right, keep on increasing. So this is not alpha power k, it's alpha power m. Okay, as you increase m, this will go down to 0. That means the correlation from, for example, if alpha is 1, what is it saying? It's saying if you take a signal like this, right, and if you take, this is your time axis, and if you take a point here, okay, this is, let's say, t, and you take a point which is like t plus m, and this is m, right? As and when m increases, the correlation between x of t and x of t plus m will go down to 0. It becomes almost independent. So the interesting thing about this is I can sort of assume that this random variable and this random variable are independent. Okay, so that you can use those facts to prove some sort of a law of large number kind of a result. Even here, even if it's correlated, still I can prove because they are independent, approximately independent. So I can replace this by independent random variables. So and apply law of large number. So it sort of mixes well. It becomes decorrelated after some time. Okay, that is true provided alpha is less than 1. If alpha is equal to 1 or greater than 1, it is not true. Okay, is that okay? Any questions? Okay, so I think I'll just state what, maybe I'll do it in the next class. So there is something known as stationarity. So what it essentially means is that if you take a k points, okay, x of t1, x of t2, and so on, x of tk. Of course, it's jointly Gaussian. It has some distribution, but if you shift the entire thing by any tau, right, the distribution doesn't change. Then we say that this process is stationary process. Okay, it should happen irrespective of what k points you pick and irrespective of what tau is. Okay, that's called stationary, and we'll see what is the condition under which Gaussian process is stationary process. It turns out that you just have to the covariance function doesn't depend on 2 points u and v. It only, or t and tau, it depends on the difference. Okay, t minus tau or tau minus t. Okay, so that's called. Then we can use that to define what is known as white cell stationary for a general stochastic process. Okay, once we do that, we will see how to construct a new or a Gaussian process using IID Gaussian random variables. Okay, that's where we need. Okay, just to give you a prelude for that, which we'll see in the next class. Let's look at this. Okay, x0, x1, etc. IID Gaussian with zero mean and variance sigma squared. What I'm going to do is I'm going to do this. Okay, I equal to 0 to infinity xi. Okay, so I'll just use phi I of t. What is phi I of t? This is a set of orthonormal functions. You know what an orthonormal function is? Functions are? Huh? Can somebody tell me what is an orthonormal function? What is an orthonormal function?
It's orthogonal to all other functions. And
what do you mean by that? Orthogonality means what?
Integral of
phi
Yes.
I.
yeah.
Right. So integral of phi I of t times phi j of t dt over a period is 0, right? For all I not equal to j. If I equal to j, then we'll get 1. That's called an orthonormal functions. Right? Where is it used? Fourier series, right? For example, complex exponentials with the integral multiples of frequencies, it corresponds to an orthonormal, well, orthogonal functions. When you normalize it, you'll get orthonormal functions, right? So essentially, you do a Fourier series, you write the Fourier series expression with Fourier coefficients being drawn from IID Gaussian with zero mean and sigma squared variance. Then we get a Gaussian process. That's one way of constructing a continuous time Gaussian process. So far we have looked at a discrete time Gaussian stochastic process or Gaussian processes, right? This is how you define or get a continuous time one. Okay, so we will see how to do that and what are the consequences and what happens if you pass that through a filter. So some of these things we will quickly go over, and then we will start Wiener process. So I want to do Wiener process in slightly more detail this time. Okay. Yeah. So once we do that, we will move into Markov chains hopefully not by the end of next week or the week after that. We'll start Markov processes. Okay. Is that fine? This sort of covers wide spectrum of tools that you will need as a researcher. Okay, you need Poisson process, you need Gaussian process, you need Wiener process, you need Markov process or Markov chains, right? So all these are very useful tools in engineering, especially electrical, that too in signal processing, communications, and machine learning. Okay, so I'll stop here. Any questions? Yes, any questions? Ayush, you have any questions?
No, sir.
Yeah. Maybe I'll just quickly correct this. What went wrong? Is this correct? X of n plus 2 is alpha times x of n plus 1. I think this is W of n, right? It's not, yeah, it's, let me just write the way I have written this. W of n plus 1, you have n. So n plus 1, this is correct. Okay. And alpha, x of n plus 1 is alpha square times x of n, that's correct. Plus alpha times x of W of n, that is correct. And W of n plus 1, this is correct. So x of n times this is correct. Alpha times x of n W of n, times alpha, this will be W of n plus 1. X of n times W of n plus 1 is 0. X of n times W, x of n has W of n minus 1, so this is also 0. So we only need to take alpha squared x squared of n. So this is, so this gives me alpha squared expected value of x squared of n. So this is nothing but alpha squared expected value of x squared of n is what? This thing, right? Each square I have to consider, but the cross term will be 0. So W squared, the first term squared is sigma squared. This is alpha squared is sigma squared, and so on, right? So that's what we have. So I think that's fine. Yeah. Alpha squared, sigma squared, and you have, sorry, this is 1 alpha squared, alpha power 4, alpha 2 power n minus 1 sigma squared. So now alpha squared, sigma squared, 1 minus 2n divided by 1 minus alpha squared. Okay, this is fine. You need not check. Okay. Okay, I'll stop here then. You know the mistake, right? So it should be squared, alpha power 4, because we are squaring it. Okay, take this as an exercise and figure out. Okay. Any other question?
Hello,
Yes.
sir, can you go to that slide?
Yes.
The x of n above. Yeah, x of n equals W.
Correct.
Down, sir. Still down. This one. Sir, here we can use the fact that since Wn minus 1, n minus 2 are independent, we can use the, since we know that variance of sum of random variables, independent random variables.
We have done. Yes. So
We can do. We could have used it directly here.
The variance of the sum is nothing but the sum of the variances. So this will give me sigma squared. This whole thing will give me alpha squared sigma squared, and this will give me alpha power 2 times n minus 1 sigma squared. So when you add them, you get that expression. It's a geometric series, right, with the alpha squared term instead of alpha. So okay, that's how you get that expression. So you can generalize that. It's pretty straightforward. Okay, any other questions? So we will have another quiz or whatever you want to call it, mix and whatever. So not the coming week, the week after that. Okay, I will let you know by Tuesday, but start preparing for that. Okay, the syllabus will be whatever I'm going to teach till the end of next week. After quiz, sorry, whatever that the first chapter was there for quiz. So after that, the second chapter will be there for the Poisson process and all that, plus the Gaussian. So that will be there for the next quiz. Okay. Okay. Yeah. I'll stop. Thank you. Any questions?
Thank you, sir. No, sir.
Okay.